In this video, we're going to do another example of analysis of variance. And here we've got an example which has a set of circumstances, so it's not generic. And we are going to use R, of course, to do the lion's share of the computations, but we also need to put in our own work in establishing the hypotheses and interpreting the output from R. So here we go. 12 lambs were randomly assigned to one of the 3 experimental diet programs. A graph of the weight gained is shown. Is there a significant difference in the average weight gain across the diets? I've got the data input here into R, but before we go into R, I want to ask some questions, and I want us to anticipate our conclusion by looking at this image here. So we've got the weight gain graphed across the 3 diets, 1, 2, and 3. R alphabetized them because of the way the data was organized. That's okay. I would like you to notice some of the variability in this set of observations. For one, how spread out is sample number 1? How spread out is sample number 2? And how spread out is sample number 3. All right, so a fair amount of spread, or it at least appears that there's a fair amount of spread because the other set of variability worth considering is how spread out are the sample means. Now I don't have the sample means available here, but I could if I wanted to. I just went and found them out. It was 11 for sample 1, 12 for diet 3, and 15 for diet 2. Okay, so how spread out are these sample means from each other in comparison to the spread within the samples? Right? Not that much, right? There appears that the sample means, certainly they're different, but they are not that different because of how much variability is within the samples. That is analysis of variance. Here, the variability across the groups in pink is small when compared to the variability within the groups in blue. Another way to consider that is notice that the observations, there's a lot of overlap among them, right? There's a lot of overlap. All of that put together, I believe, allows us to anticipate our conclusion that we will most likely not reject the null hypothesis here. Okay, now before we go and do analysis of variance in R, I want to ask a few more questions. We'll write down our hypotheses as well. Okay, I'm back. So let's identify the response and explanatory variables in this study, and then we will declare the null and alternative hypothesis. I think it's useful to identify our variables here because it's going to help us state our hypothesis and ultimately our conclusions. Okay, well, what was the response variable? What do these values, what were they measuring? Now, we were only given a brief description here, but this is the weight gained based on 3 different diets. So these measurements are the weight gained. Now, what's the explanatory variable? I think this was in pounds, but it doesn't say though. The explanatory variable was the different groups, and there are 3 groups here. So that would be diet type or type of diet. Now that we've got that out of the way, let's write down our null and alternative hypothesis. H So ANOVA, like the two-sample t-test, we want to see if the means are equal. And here I'm going to say the mean of diet 1 equals the mean of diet 2, population mean, not sample mean, mean of diet 3. In the alternative hypothesis, a common mistake is to say that they are all different. That is not what needs to happen in order to break that string of inequalities. For the alternative, we say that at least one of the population means, population mean what? Weight gains, is different. Different among what? Different among the diets. So in the first video of this series, we did a very general example of hypothesis for ANOVA, but here we've got it all explicit given the study variables. Okay, next step. Now let's use R to perform the analysis of variance at the usual 5% level of significance, and then based on that, we will state two conclusions. Will we reject the null hypothesis or not? And we'll provide an interpretation. Here we go in R. We did this in the previous video, but here we go again. The way that we do analysis of variance, we do AOV, analysis of variance. And it is the response variable, squiggle the explanatory variable. And it's a little easier in my perspective to give that a name. And then in your next step, you would say, all right, give me the summary of that name. And then that's going to get you the ANOVA table to which you can go find the p-value to. Because we identified our response and explanatory variables, hopefully that makes it quite easy to do this. I'm going to call this, I call the data frame lamb. We've got weight gain, we've got diet. I'm going to call this sheep. AOV, the values need to come first. So that is the vector called weight dot gain. Remember, those capitalizations make a difference. Squiggle lamb dollar capital D diet. Okay, that's great. Now I'm going to ask for a summary of sheep. And there is our ANOVA table. And as expected, again, right up top, we said we probably were not going to reject the null hypothesis, and here we are. So if this was a lab assignment, I would probably ask you to copy and paste everything that I've highlighted here, so I know what you've typed and can make sense of what you've done. In this little example, though, it's going to take up a little too much space to do that. So let's state our conclusion and be sure to mention the study variable. Since our p-value is quite large, 0.491, and that is greater than 0.05, we do not have evidence or support to reject the null hypothesis. Now, to translate that within the context of the problem, I would say there is insufficient evidence for the alternative hypothesis. Maybe not enough evidence to claim that at least one of the mean weight gains is different among the diets. A couple more points I would like to say. When we do not reject the null hypothesis, we generally say that there is not enough evidence for the alternative. If this entire problem was completely different and it was a conclusion of we do reject the null hypothesis, I would just delete these two letters right here. And a note about error types. I've noticed a little bit of issue with interpreting types of errors. We never know if an error is made, right? We're not talking about a symbolic error or a mathematical error. We're talking about an error of sampling. Do these samples, are they representing their respective populations well? And we hope so. Random sampling, randomized experiment, but there's a possibility that's not happening. There's a possibility that this conclusion was based off of a sample that, because of sampling variability, is not a well representation of its population. So because we failed to reject the null hypothesis, we could have committed a type 2 error, but we do not know. That'll do it for this example.